Hi, I'm Jack Connors, and I'm presenting Searching for Pulsar Glitches in NANOGrav Data. Neutron stars are formed when a star ends its life by exploding as a supernova, and they are very dense and very compact. So compact, in fact, that the protons and the electrons get crushed together and they become neutrons. And a pulsar is what happens when the very strong magnetic field of a neutron star focuses the radiation from the neutron star into a beam that rotates with the neutron star very rapidly, and when that beam passes through Earth, we observe it as this regular periodic flickering on and off in the radio waves, like a lighthouse, and that's what we call a pulsar. And the North American Nanohertz Observatory for Gravitational Waves, or NANOGrav, is using an array of pulsars as clocks to search for gravitational waves. And the pulsars can be used as clocks because they have a very regular periodicity in their pulses, especially the millisecond pulsars, which are old and stable, but they don't reach the Earth in a perfectly periodic manner, because, as you can see in this diagram, the pulsar is moving possibly around another object, the Earth is moving around the Sun, and there's an interstellar medium that can disperse the pulse, and we can create a model of all of these effects that will allow us to figure out how the pulses actually left the pulsar and what the period actually is. So, with regards to millisecond pulsars, which are the type of pulsar that NANOGrav uses, that have a pulse every few milliseconds, I searched for glitches in the pulses, the times of arrival of the pulses, and what a glitch is a sudden change in the period of the pulsar's spin, and therefore in the times of arrival of its pulses. And one way to cause a glitch is to have a parcel of fluid from inside the neutron star just suddenly shift outward like a starquake. And the reason this is important to NANOGrav is that if a pulsar glitches, it would make the clock inaccurate. The clock that the pulsar is used as would be inaccurate. And because millisecond pulsars are old and stable, it's expected that glitches would be rare, but it's still important to search for them. Okay, so the program that I use to search for glitches is called Pint. And what Pint does is it compares the data collected from the radio telescopes of the times of arrival of the pulses, which are basically the ticks of the clock, and compares them to the model that predicts all of the effects that could make it not perfectly periodic, like the motion of the pulsar, the motion of the Earth, the interstellar medium, and subtracts the model from the data and generates this residual. So if the model fits the data very well and we know what is happening, we would get something like this particular residual, where everything in it kind of hovers around 0. So to figure out whether or not a pulsar has a glitch, we test whether or not the model becomes significantly better if we add the parameters describing the glitch versus without those parameters. So one parameter that is related to the glitch is the second order spin down. So the first order spin down tells us how the pulsar is slowing down over time, because pulsars do slow down over time and they lose energy. But the second order spin down tells us an acceleration of the slowing down. And for these 3 pulsars, I fit a model to predict what the second order spin down, or F2, could be, and then used a statistical test called the AKK information criterion to determine the ratio of the odds that F2 is a significant part of this pulsar versus not. And I tabulated those odds in this table down at the bottom of the slide. So for example, this would mean that B1855 plus 09 is 1.72 times as likely to have F2 as not to have F2. So some further work that I would do is I would add the rest of the glitch parameters and do another statistical test called the F test, which is more accurate because instead of producing these odds, it would allow me to actually accept or reject the model. And instead of only doing 3 pulsars, I would check the entire 12.5-year data set. Well, thank you for watching my presentation. I hope you enjoyed it. Please leave questions and comments below.